Velocis is changing the way the world produces energy with microchannel process technology. The gas-to-liquids or GTL process is a prime example. The gas-to-liquids process begins with steam methane reforming, or SMR. Shown here is a reactor assembly which can hold up to 10 microchannel steam methane reforming reactor blocks. A conventional box furnace reactor with an equivalent capacity would be 10 times larger. The reactor housing encloses a number of reactor blocks, which are connected by headers which are shown as colored. Air and fuel are introduced into separate headers, while natural gas or methane is co-fed with steam in the process header. These headers evenly distribute flow to the reactor blocks housed within the assembly, as well as collect the synthesis gas produced. Inside each reactor block, proprietary manifolds uniformly distribute flow into thousands of microchannels. The architecture contains many identical repeating units, consisting of channels for each of the inputs, air, fuel, and reactants, and outputs, exhaust and synthesis gas. These channels form repeating layers within the steam methane reforming reactor blocks. Process channels form a U-shape, where both inlets and outlets are located at the top end of the reactor. Relatively cool gases enter and leave the top, while the reactions occur at the high-temperature lower end. The combustion and reforming catalysts are applied in the microchannels only where needed. On the combustion side, air and fuel enter in parallel channels. These streams are preheated by recuperating heat from the exhaust gases leaving the reactor. Temperature increases rapidly, moving toward the bottom of the reactor block. Air and fuel mix at the hot end and combust catalytically. This method of combustion minimizes unwanted byproducts, including oxides of nitrogen, commonly referred to as NOx. The exhaust stream makes a U-turn and exits at the top of the reactor. Heat from combustion is used to drive the equilibrium-limited steam methane reforming reaction, which is most effective at temperatures above 850 degrees Celsius. In the process channels, steam and methane are converted into synthesis gas or syngas, which consists primarily of hydrogen and carbon monoxide. While exiting the reactor block, the product gas exchanges heat with the incoming methane and steam. Combustion exhaust leaves through the stack on the top of the assembly. Synthesis gas exits the assembly through a manifold similar to the inlet headers. The next major unit in the gas-to-liquids process is Fischer-Tropsch or FT synthesis. Microchannel technology also improves this step. Conventional FT reactors can tower to over 200 feet tall or 60 meters, while microchannel FT assemblies sit horizontally and measure only 5 feet in diameter and are 25 feet long or 2 meters in diameter and 6 meters long. Headers pipe in coolant water and synthesis gas and evenly distribute flow to 10 reactors in each assembly. Liquid water flows horizontally into the cross-flow microchannel FT reactors and exits as a two-phase mixture of water and steam. The steam is vented through the top of the assembly. The synthesis gas flows from top to bottom and leaves the reactors as FT products, a synthetic crude containing a mixture of longer-chain hydrocarbons. This is a view of an individual FT reactor block. Inside each reactor block are thousands of microchannels. Again, coolant water enters on one side and leaves as steam on the other. The reactor has a cross-flow structure. Synthesis gas flows vertically downward through the process channels. As the gas passes over the catalyst, up to 70% is converted to FT products, which include naphtha, diesel and jet fuel, and paraffinic waxes. Crude FT products flow from the reactor assembly in a single pipe, leaving the catalyst in the reactor blocks. In some competing technologies, the catalyst flows out with the FT products and requires separation after the reactor. The resulting product is an ultra-clean, high-quality synthetic crude. For offshore facilities, this product will be blended with petroleum crude and transported via conventional shipping infrastructure. For onshore facilities, there are many high-value options for FT products. For example, hydrocracking can be employed to maximize diesel or jet fuel production. Microchannel process technology greatly improves the gas-to-liquids process and is just one example of the way Velocis is changing the way the world produces energy.